Welcome. Let me just tell you about a few computations of curvature for manifolds and about the construction to get new manifolds from old manifolds, which is the well-known connected sum construction. We have the level surface construction, which allows us to get new manifolds, but that's also very convenient. And this week I was doing some experiments with those. So here's the theory. I'm not repeating it. It's very simple. It's essentially the complexity of Euclid's axioms in planimetry, but it's all about all manifolds. It's essentially PL geometry, piecewise linear geometry can be covered with this in any dimension. And there is some topology, finite topology. Everything is finite. We don't like infinity. Everything is finite. There are a finite set of sets, and we are having very beautiful structures like this hyperbolic structure. I'm coming from dynamical system. Hyperbolic structures are important. And by the way, just here, getting back a little bit into hyperbolicity by looking at manifolds which have negative curvature. So the curvature which we have defined is really doing the right job. It produces positive curvature if we expect it, and produces negative curvature if we expect it. And so this is a sectional curvature. It works in arbitrary dimensions. I have here one of my favorite examples. It's kitsch, it's overused, it's pop culture, because it's soccer balls, right? If you have a soccer ball, it's there. A soccer ball dual is the pentakis dodecahedron, which is a triangulation of a sphere. So that's a nice simplicial complex, a very beautiful object. But it's not as boring as the icosahedron, because we have also degree 5 and degree 6. So what happens, it's not part of this Mickey Mouse structure. I proved once a theorem in arbitrary dimension which says if you have a positive curvature manifold, if this curvature here, the sectional curvature, the naive sectional curvature, that every embedded wheel graph has positive curvature, that's a very, very strong condition and forces the manifold to be very small, too small, for example, to get projective spaces. That's not the case here when we look at this more sophisticated way and the curvature, sectional curvature. Of course, when you look at the two-dimensional situations, it's a curvature which adds up to, which has a Gauss-Bonnet result. So in 2 dimensions, this is just a curvature which works. It's a form curvature. It's actually an average of a form curvature of a curvature we have looked at before. But it's the simplest possible way we can define sectional curvature. So we have a manifold, arbitrary dimension. We want to define a 2-dimensional direction, and the 2-dimensional direction is given by the bones, a Q-2 simplex. This defines us then a structure like this, which is called a sheet, a geodesic sheet, and we can then compute the curvature of this geodesic sheet. And so that's more sophisticated than just looking at the vertex degree of a embedded 2-dimensional space. So it works very well, and we can also look at the geodesic flow, which is interesting. So I was looking at every manifold. I can compute, make a statistics about the geodesic flow. For example, here in this case here, this is a very symmetric case, beautiful case where all geodesics have the same length. So it's a kind of it's an example of a manifold where all the geodesics have the same length. It's a fancy topic in the continuum. And we have the curvatures is 1/15, 1/18 in this case, positive. So even so, there are degree 6 vertices, and so it has positive curvature. I was making also some experiments with suspension and double suspension, etc. So you can get from a suspension, you get the 3-sphere, double suspension gives you a 4-sphere, and so on. You can look at higher dimensional manifolds like that, and they appear to have also here positive curvature. So it's nice that works, even so, a 3-sphere has Euler characteristic 0. Of course, these sectional curvatures don't add up to Euler characteristic. to be expected, because that's also happens in the continuum. If you take a 3-sphere, round 3-sphere, then we have positive curvature, constant curvature 1, but the Euler characteristic is 0. So just about this example here, I love kitsch. It's overused things which appear in every presentation about polyhedra. This is probably one of the most used polyhedron also by nature, because it appears in chemistry as Buckminster Fuller-Rehne, and in architecture as geodesic domes by Buckminster Fuller, who was a architect, was born close by. The soccer ball, right? It's sports. Soccer balls are made like this, patches of 5 polygons, 6 polygons with 5 and 6 vertices. It's also used as cages in biology to proteins, and it's used. Was also used. A bad use was the Fat Man bomb had this structure, pushing all this explosive together. So about the connected sum, there are different ways how to build connected sums. So you can take the simplest cases. You take 2 simplices, one simplex in one manifold and one simplex in the other, and you glue them together and you remove the inside of that simplex. That works in the class of simplicial complexes. So here I took 2 small tori, the smallest tori I could find, the simplicial complexes. They are not Whitney complexes, so 8 vertices. And the torus, a 2 torus with 8 vertices is very, very small. You cannot realize that as a graph. So in this case, the sectional curvature is equal to 0, and now we can look at the connected sum of 2 such small tori, and then we get a genus 2 surface, and in this case the f vector is 13, so this genus 2 manifold has 13 vertices only, and here are the curvatures computed with this formula. So negative curvature, which is kind of nice to have negative curvature manifolds. Right? The Euler characteristic is -2, so it's nice to have actually a negative curvature manifold. So the geodesic flow in this case, that's also to be expected, because we know in the continuum, if you have a negative curvature manifold, the geodesic flow is ergodic, hyperbolic. It's very complicated, so there are essentially ergodicity means there is just transitivity, and in this case we just see kind of two very large geodesics in the frame bundle, and then there are short ones, which is also to be expected because we have small closed geodesics, right? So 1, 2, 3, 4. So somehow they appear here also in the discrete. Now I was also kind of taking 2 projective planes, which is nice. So the smallest projective plane as a simplicial complex, which I could find, has 6 vertices only. So again, this is not something you can realize as a Whitney complex of a graph. For a Whitney complex of a graph, you have to take the complement of C7, which has 7 vertices, and then you glue a disk on it. So you have 8 vertices. So this is smaller than the smallest Whitney complex. And that's, by the way, a reason why in the graph case, so small manifold case, you cannot have other interesting examples. So we cannot build a projective, we cannot embed a Möbius strip, we cannot turn around, we don't have space to turn around if we kind of force every real graph to have 5 elements. So we need more space to turn around. So this is a Klein bottle, which is a connected sum of 2 projective planes. It has a Euler characteristic 0, but the curvature we can compute, and in this case what I got is the curvatures in this case is either 1/60 or -1/30. Of course they add up to 0. And maybe that's it for today.